Perceptron is an interesting algorithm, and one of the first we're learning was probably convergent in a separable case. But there are a couple of weirdnesses that we want to correct about it, would like to correct about it or improve. So one of the things is the following. Okay. One thing is if we have a linearly separable data set, and let's say this is actual data, so we are in let's add another one, in empirical risk minimization settings. We can have as many solutions, or perceptron algorithm can have as many solutions as it wants, or infinitely many, rather. All of those hyperplanes will be the perceptron solution. We can arrive just by chance, randomly starting somewhere at any of them, and it's fine. And so some of the solutions will be too close to the red class, some of the solutions will be too close to the green class. Is it possible to, oops. Yeah, is it possible, or would be nice, right, if we could intuitively say, well, imagine we placed, looking for some color, we placed our solution hyperplane right here. Well, this point green is still on that side. Consider this imperfections of my drawing in the screen, but it's still on this side. So what if we just didn't collect enough data and it's a mistake? There is, yeah, okay, go green. The actual data set is like that, right? So the same goes backward to the red class. What if we put our solution too close to the red class, but the data that we collected is actually slightly over? So intuitively, but we will talk later in the class about proper proofs for that, proper considerations. Intuitively, it would be nice to put a hyperplane somewhere in between, in the middle, so that if, okay, let me kill it all, somewhere in the middle, so that if we failed to collect the data correctly, we're still kind of leaving some gaps. So some green can still go here, some red can still go there. So yes, indeed. And again, renaming, this is our W, and the Y's are our label time XI. I mean, I never used the Y's in the previous slides just because it's yet another thing to remember and to talk about. So margin tells us that we'd like to have a region in which we don't allow, a solution region in which we don't allow any points. So for example, from one of our previous examples, if this is a separating hyperplane and our points ended up here, the y points, or label times x, but we have a margin, we don't want these points to be too close, we will shift our hyperplane over here. This is not a vector, this is just showing you a picture, so that our margin is large and there's nothing here. Effectively, if we flip the sign of those points back, they will be on this end of the hyperplane, and it's kind of, we're adding, let's come back. with respect to here, we're adding some cap around, or some sorry, same color. So we're adding some region, some stripe of where the points are prohibited. So that is our P, our margin. So for various points, for various y's, those margins will look differently, but or how far they are allowed to be from the hyperplane, solution hyperplane. So indeed, we can take the stochastic perceptron algorithm and reformulate it to work with the margin. We define how much we want the margin to be. So like this gap that the points are not allowed to be within vicinity of the separating hyperplane. Now we define the learning rate and threshold, and then our incorrectly classified samples are those that are closer to the hyperplane than this gap P. So we have hyperplane that we're going to use on new data, and we hope that it will generalize better if it's not too close to our training data, that there is a gap P. So it's not less than or equal to 0, it's actually less than or equal to B. So from either side, because this negative for either positive class or for negative class, if they're classified incorrectly. But even when they're classified correctly, but they're too close, the point is too close to the hyperplane, this condition will trigger. And as before, and notice just our J criterion was LIW transpose XI for XI in the set of incorrectly classified samples. So this is nothing but the gradient for that particular sample, right? If we take derivative of J with respect to W, we get nothing but so we're doing this gradient descent, and yeah, we can minimize this objective with the margin now, with the margin B. So in the hope, no theoretical proofs yet, but in the hope that we can do better in practice. And our stopping criterion is that when everything is away on the right side, on the correct side, and away from the separating classifier plus the margin. So remember before we just had greater than zero for all of the samples. That's one generalization. A hack, but a beautiful one, and it works. Another one is, yes, look at this objective criterion. What is the problem with it? Well, the problem with it is that it's discontinuous. So it's highly discontinuous, and we've seen that the points will be jumping back and forth, or the steps will be jumping back and forth. I will show that to you in the next section. So, and that's not too nice. We would like to have something smoother, and we would like to be able to optimize other criteria than just simple perceptron objective function or perceptron criterion. And we can do that if we define our loss as this expression, which is nothing but we still have our margin. We want to deal with the margin because it's useful for generalization. That's how intuition goes. But instead, I reproduce our previous criterion. Incorrect. Still incorrect. L I X transpose W. I mean, they're symmetric. Anyways, so that this is our previous criterion. We're normalized by the length of the the norm of the sample, and we're added our margin. The gradient, if we differentiate it with respect to w, will be this. Well, this is a quadratic function with respect to w, so we get a linear gradient with respect to w, and it's still a vector. The objective, the criterion, is a scalar, so it's a function that takes a vector, returns a scalar. The derivative is a vector, as we discussed before. Easy. And then we just use this derivative as before. Right? So this is our derivative. We were using perceptron derivative before, which is minus Lixi, and we were minimizing that objective function, so the minus turned into a plus. But now we have a learning rate which can have the negative sign jumping back and forth. So we flip them. That's how that's where the negative sign went, and we have the same perceptron with margin, but now with a different objective function that is smoother than the original one. And the smoothness, well, the original one was totally discontinuous. The smoothness has a geometric interpretation. So we have RK, if we define RK as this ratio, which is our derivatives without the additional LKXK. Then RK is the difference to this hyperplane, which we know this hyperplane is defined by YK. Again, reminder, YK is LK times XK. It is our modified data sample that's scaled by the label cyclic, basically -1 or 1. But now this new hyperplane here on the figure is a function of W. So the normal YK or XK times LK is the normal to that hyperplane, and all of the W's or A's here, all of those W's will minimize our solution. Will minimize all of the W's that feed the equation, that make the equation equals B, feed the solution. And by doing gradient descent step in eta times RK, we're actually taking our current W and smoothly moving it towards this hyperplane. Any of W's on this hyperplane would satisfy the solution for which this Y is correct. Well, anyways, so that's perceptron relaxation procedure. It relaxes the discrete non-smooth objective function of the original perceptron algorithm and makes it smooth and nicely behaved with a margin so that perceptron generalizes better.